Hello guys. Today we'll be discussing with RCC design. So first of all, what do you mean by RCC? So this RCC basically has three letters. So first one is reinforced. Okay. So what do I mean by reinforced? Basically, it's the steel which is provided in the concrete. Then C stands for cement, and then the third C stands for concrete. Basically, when I say RCC, it's a mixture of reinforcement and concrete which is prepared with the help of cement. Then, then this comes to my next question. So why specifically reinforcement and concrete? You know why? Because personally I prefer to call these two, reinforcement and concrete, as a jodi of Jay and Viru. Jay and Viru are famous jodi from our Sholay movie. The reason why, because these two, the reinforcement and the concrete, they complement each other. How do they complement each other? What are the properties of reinforcement? Basically, what are the properties of steel? It has good tensile strength. And when I say concrete, what are the strength of concrete? The first thing is compressive strength. But when I say compressive strength, that doesn't mean that for reinforcement that compressive strength is very less. But since if the size of reinforcement reduces, the compressive strength reduces. But whereas that is not the case for concrete. Okay. Then what is the next property for concrete? It is easily workable. Now, what do I mean by workable? By workable, I mean that concrete can be cast inside. It can be prepared by mixing cement, aggregate, and sand on site, and then it can be cast inside. And it is very much more of a something between liquid and solid. So it can be directly transported and put in the place. But that is not the case for steel. Steel comes in a specific size. You will have to transport it. So the transportation becomes a bit difficult. And then, okay, fine. These two are complementary. They have some properties. Steel has some property. Concrete has some property. But then again, why Jai Viru specifically? Because if you see, their friendship is very much known to everyone. So if you see, almost all the structure will have these two components, reinforcement and concrete. So that is why I prefer to call them as Jai Viru Jodi. So now when I say about RCC design, so there are two famous theories. One is working stress method. Basically, this is the method. It's an old method right now, and we don't follow it much in the industry. And the second method is limit state method. Okay. So when I talk about RCC design, we'll basically be following IS 456. So IS 456, the present code deals with the limit state, and the previous code, which is now discarded, deals with the working stress method. Now, what is the difference between working stress and limit state? So basically what happens in working stress is that the load which is applied on the structure is as it is. We do not increase the load, we do not decrease the load. We keep the load as it is, and then we reduce the property of the material. So basically material means we have concrete and we have steel. So what we do, we apply a factor of safety and reduce the property of the concrete. So when I say in working stress method, for a beam, the concrete strength, if it is M20, it is divided by 1.78. So this is the factor that we use for reducing the strength of the concrete. And for steel, the factor goes as high as 3. So in working stress method, we keep the force as it is and we reduce the strength of the concrete and steel. But what happens in limit state? So limit state, basically the word goes limit. In this, we increase the force also. So basically, if whatever force is applied on the member, so we increase the force by multiplying by a factor, and we also reduce the property of the, let's say if it is yield strength. So we also reduce the strength of the material by multiplying by a factor gamma s. Okay. Now when I say limit state, so basically what I intend is I go to the limit of failure. Now failure can be of two types. The first one can be collapse. Collapse, basically a structure or a member, not exactly the complete structure should collapse, but even a single member. Let's suppose if I am designing a complete 2-story building, and even if a single member fails, so that is collapse. And the other one can be serviceability. Basically, by serviceability, I mean the structure is not completely collapsing, the structure is standing on its own, but it is not in a condition that it can be used for serviceable, for whatever purpose is there. Let's suppose, for an example, if I take a water tank, the water tank, we have designed it, but in the walls there are a few cracks developed, and the water is coming out of the water tank. So does that mean the structure has collapsed? No, it has not collapsed. But what has happened? It is not serviceable. It is not serviceable means the water which was supposed to stay in the tank is leaking out. Okay. So when I say collapse, so there may be different ways by which a structure can collapse. So the first one can be flexure. Where do we find flexure? Basically in beams, slabs, where the load is acting. Let's suppose this is the member, a load is acting something like this, and the member is bending in the perpendicular direction to the load, in the direction of the load. So that is called flexure. Then another kind of failure can be shear failure. What do you mean by shear? When the load is applied, the member fails directly from it, a straightaway failure. So that is shear failure. Then there can be another type of collapse, which is compression. What is compression? If a member is standing straight and the load is applied in this direction, in the direction of the member, so that is called compression. If you want to remember how compression can resemble, do you remember a umbrella which was used in the previous days by our grandfather? So they used to have an umbrella something like this, and it used to have a shade like this. And when they used to fold it, they used to keep it on the floor and they used to walk using that umbrella. So at that point of time, the compression load was acting. So that is the best example to understand what compression can be. Then the last one is torsion, a notorious kind of a force, I would say. Notorious as in because it's not very easy to comprehend, it's not very easy to resolve. The reason being, first of all, how do you understand torsion? Let's suppose I have a member like this and I twist it, I apply a force perpendicular, something like this. So this is called torsion. How? This is the member and a force is applied in this direction. Basically, we are twisting the member. So that is called torsion. Okay. Now when I talk about serviceability, what kind of forces, what kind of failure can be there in serviceability? The first one we discussed right now, crack. A member which was supposed to have less amount of crack but has cracked more than its allowable limit. Then there can be issues like deflection. How can deflection be a critical criteria? Do you think so? Yes, it can be. Let us suppose there is a beam, and below the beam there is a wall. If this beam deflects, there will be a force acting on this wall. This masonry wall, which was not supposed to carry any load, is applied with a load which is coming from the beam, and because of that the wall can crack. These walls, the partition wall which is there in your building, can crack. So deflection becomes an important criteria, right? And another thing which can lead from deflection is, if there is a deflection, there may be a possibility of crack, and because of the crack, the structure, the reinforcement get exposed. Okay. And then what can be another kind of serviceability criteria? Deflection of the overall member. This I'll call as deflection local. This I'll call as deflection global. What do you mean by deflection global? A structure which is standing, if there is a 5-story building which is supposed to be standing something like this, and it gets swayed like this, and the way it gets swayed, that the deflection, although this deflection which is happening at the topmost story is not affecting the overall structure, but it is affecting the person who is residing in that story. The person who is residing in the story is not feeling comfortable because of the sway. So that is again a serviceability failure. We do not want a person who is residing in the structure, in the building, to have uncomfortable feelings. Okay, so this is how it's about limit state of collapse and limit state of serviceability. Like we discussed that in limit state of theory, we'll be applying a load factor to our design load. So our design load is scaled up. How is it scaled up? Basically, if I say FD is my design load, so it is F characteristics, which is the characteristic load. I'll tell you what characteristic load is, and it is being multiplied by a factor gamma F. So my force, this factor is basically scaling my force. Okay, how we'll come to know about this gamma factor? We have a standard code for this IS code. It's IS 875. Okay, so we'll refer this code for different kind of factors which is to be applied for the loads. And now when I say FC is basically characteristics load. So how do we calculate characteristics load? Basically characteristic load, if I define it as, this is the load which has a probability of more than 90% of exceeding in the lifetime of the structure. How do we calculate this 95% probability? If I, let's suppose, if I plot all the loads which can exist in the entire structure, it more or less goes in the form of a bell curve, something like this. Okay, this is a very famous curve. It's a bell curve basically. If I call it, this is a bell curve. Okay, where this is the point which is called as mean point. And if I say FC, if I have to plot FC where it is on this graph, I'll find it somewhere here. Okay, so basically a force which is there, this force, this value I call this as FC, this force has a probability of more than 95% of exceeding in its entire lifetime. How do I calculate FC then? From basic principle of statistics, basically FC is Fm plus K times S. Now what is K? K is basically a factor for certain kind of probability. For 95% probability, K is equals to 1.65. Okay, and what is S? S is standard deviation. Okay, how is standard deviation calculated then? Basically, standard deviation is calculated, it is square root of sum of any force, any value. If I take from here this value, or maybe this value, or maybe this value, any value which I take and I subtract it from Fm, square it. The reason I have squared it, because if I don't square it, there will be some value on left side of the mean, some value on the right hand side of the mean, and these two will cancel out each other. So we don't need to cancel out these, and it will be F minus Fm whole square divided by number of samples which we have taken. Okay, to understand this, let us have an example. Let us take some example. Let's suppose there is a member which has an applied load of 30 kilonewton per meter, 20 kilonewton per meter, 25 kilonewton per meter, 40 kilonewton per meter, and 35 kilonewton per meter. Okay, now we have these 5 samples. Okay, so we need to calculate the characteristics load for this. To calculate the characteristics load, first we need to calculate the mean load. Now, what is mean load? Basically, it's the average of all these numbers. 30 plus 20 plus 25 plus 40 plus 35 by 5. This is basically 550, 437, 89, 10, 11, and 314, and 115 by 5. So my mean comes out to be 30 kilonewton per meter. Now I have to calculate the standard deviation. Now if I calculate the standard deviation is basically square root of sum of, first number is 30 minus 30 whole square plus 20 minus 30 whole square plus 25 minus 30 whole square plus 40 minus 30 whole square plus 35 minus 30 whole square divided by n minus 1. Remember, this is also in the square root. Okay. Now, if I calculate this value, for the first term comes to be 0 plus 10 square is 100, 5 square is 25, then again 10 square is 100, and then 5 square is 25 divided by 4. So this basically comes out to be 250 by 4 under root of this. Okay, so this is basically 5 by 2 under root of 10. So this if I consider it as approximately, it's 3.14. Is that okay? So this comes to be 16.7 by 2. So basically 8.35 kilonewton per meter is my standard deviation. Remember, this is my standard deviation. This is not the characteristics load. Now what is characteristic load? It's Fm plus K times of S. Fm is 30 plus 1.65 into 8.35. So this will come out to be something in the range of 8 and 12, something in the range of 43 kilonewton approximately. You can do the mathematics. So it's very trivial, it's basic arithmetic. So this will come around somewhere around 43 kilonewton per meter. Now, if I see this example, there are only 5 samples. Whereas when I was talking about the graph, it was a graph, which means there are almost infinite values. So what our code says, our code 456 says that to calculate this value, this characteristics load, we need to have at least 30 samples. Okay. Now on the basis of these 30 samples, we have calculated what is the characteristics load for a given condition. And these loads are very well explained in code IS 875. There are actually 5 versions. So different parts deals with different codes, different loads. First part deals with the dead load, second part deals with the live load, third deals with the wind load, fifth deals with the load combinations. Okay, so there are 5 codes which deals with all the loads which are applied on the structure. Okay, so this was all about the loads, which is how the characteristics load is calculated. Now if I talk about what are the different types of load which is there as per IS 875. So the first load which is there is dead load. The second load which is there, and I'll just talk about the general loads which are applied on the structure, will not go into the specific details. Okay. Then the third load can be earthquake load, and the fourth load can be wind load. Remember when I was saying that there is a force, design force, then it is calculated by Fc and multiplied by gamma F. This is the partial safety factor for loads. So these factors are applied with these loads in the load combination, and the load combination is given in IS 875 part 5. Okay, I'll just list down some of the load combinations. I'll not list down the entire load combination. I'll just list down some of the combination just to give an idea what kind of factor we can expect. Okay, so the first load combination can be 1.5 dead load plus 1.5 live load. So this means that when a structure is applied with dead load and live load only, then we will be multiplying with a factor of 1.5 and 1.5 for dead load and live load respectively. So this I called as gamma F. This again I called as gamma F. Now if I say that there is an earthquake load applied, so the load combination will be 1.5 dead load plus 1.5 earthquake load. In this case, what I'm assuming that only dead load is present and earthquake load is present. There is no live load acting on the structure. Now, when I say dead load and live load both are simultaneously acting on the structure, then in that case, the factor reduces to 1.2 live load plus 1.2 earthquake load. Okay. So when I consider only dead load, the factor of safety is 1.5. When I consider dead load and live load acting simultaneously, you see the factor has got reduced by some amount. Okay. Similarly, if I talk about wind load, we'll have a similar combination for wind load also. It will be 1.2 wind load and 1.5 earthquake load. Sorry, 1.5 dead load plus 1.5 wind load. Right? So there are basically dead load plus live load, dead load plus earthquake load, dead load plus wind load, dead live earthquake, dead live wind. Did you notice anything? These two are not acting together. Earthquake load and wind load. Why they are not acting together? Because the probability of occurrence of both earthquake and wind to the maximum extent, the probability of occurring both to the maximum extent is very less. So since we are talking about this FC factor, which is based on probability, which is based on that 95% probability thing, so earthquake and wind load both occurring together is very less likely. So that is why we are not considering any load combination which has both the factors together. Okay, so this is all about loads. Now if I come to strength, because there are two components in limit state, what we are doing, we are increasing the load and we are decreasing the strength. So right now what we have talked about increasing the load. Now let us talk about how do we decrease the strength. If you remember the concept which we followed for load, the similar concept is followed for strength as well. If I say this is my, or if I denote it by Fy, okay, this strength is basically Fd upon gamma m. Okay, now what is Fd? Fd is the characteristics strength of my material. When I'm talking about concrete, if I talk about concrete, Fd is basically the same thing as F minimum minus Ks. Minus Ks. Remember in this Fc, it was Fm plus Ks. Here it is minus Ks. The reason is we are decreasing the strength, we are increasing the load. Here what we are doing, we are decreasing the strength, we are increasing the load. So this is called upper bound value. Upper bound value. And this is called lower bound. If I draw a similar curve, the bell curve which we drew for the load, the similar curve will be something like this. Again, the same curve. This will be my Fm, and this will again be my F. This is my characteristic load. The load in which has in the case which 95% of my samples will pass. Okay, if this happens, then this is the load which I assume for the calculation of my strength. So this is why it is called lower bound, and this is the load which load was there on this side, so that is why it is called as upper bound. Clear? Fine. So let us take one example for calculating the characteristic strength of a concrete member. Let me take an example. If I say the samples had a characteristic strength of 30 MPa, 25 MPa, 35 MPa, and 40 MPa. Okay, let me take one more sample, 50 MPa. Okay. Actually, if you see, if the differences are very high, if I take a sample with these differences, the sample will be definitely get rejected. But this is just an example, so I'm taking these numbers. So don't take these numbers as literal values. Okay. So I need to calculate Fm first, which is the mean value. Let me draw the graph again, so it will be easy for you to capture. So this is Fm, this is Fc, 5% probability, right? Fm is basically 30 plus 25 plus 35 plus 40 plus 50 by 5. So this comes out to be 5, 5, 10, 3, 4, 5, 6, 5, 3, 8, 4, 12, 5, 17, 18 by 5. So this comes out to be 36 MPa. Okay. Now we need to calculate standard deviation. Standard deviation, the formula remains same. 36 minus 30 whole square I can write it as 30 minus 36 also. I can write 36 minus 30 also. It doesn't matter because anyway I'm squaring it. Okay. So next is 36 minus 25 whole square plus 36 minus 35 whole square plus 36 minus 40 whole square plus 36 minus 50 whole square divided by 5 minus 1. I think the numbers will become somewhat a bit random. Let's see. Let's try to solve and see how the numbers come out to be. 36 minus 36 square is 36 plus 36 minus 25 is 11. 11 square is 121. 36 minus 1 is 35 is 1. 1 square is 1. 36 minus 40 is 4. 4 square is 16. 36 minus 15 is 14. 14 square is 196 divided by 4. I think the values will come out to be somewhat random. Let's see. 6 and 7 and 8, 8, 6, 14 and 20 carry 2, 9, 10, 11, 12, 3, 15, 16, 17 carry 1, 1, 2, 3, 370 by 4. Yeah, it is coming out to be something random. Let's not calculate this there. This will come out to be some number. And then if I calculate FC, it will be FM minus K times of S. Remember, this is negative for concrete, this property, material strength, and it will be positive for loads. Okay. So this will be 36 minus 1.65 times of S. Okay. Let me see how this value come out to be. This will be 92.5, somewhere around 92. So this will be somewhere around 9.5. More or less, let us consider it to be 9.5. Okay. So this is 36 minus 1.65 into 9.5. So this will be approximately 20. So this will be my design strength. So if I have been given a sample with these values, that the characteristics, the strength are these, and this. So what I'll consider the value for my design will be 20 MPa, right? So these, it will definitely be lesser than all of these values. See, it is lesser than all of these values. Okay. So this is all about the introduction about RCC design. Now, when I said that in limit state, there were different failures. One was flexure. So let's start with flexure. Okay. And when we say flexure, so there are two different types of reinforcement. One is singly reinforced and another is doubly reinforced. So what these singly reinforced and doubly reinforced are, we'll see subsequently.